This line shows the relationship between flutter speed and Mach number for an aircraft flying at constant height. The effect of compressibility on the flutter speed may look like this, indicating flutter over a range of transonic speeds with stability at higher speeds. If the compressibility effect took this form, however, flutter would occur at a higher speed. Due to the uncertainties of calculation over the transonic range, it was decided to carry out a transonic flutter test of the Arrow wing. The transonic models were structural replicas with a thinly skinned box as the primary structure. The skins were tapered by chemical milling and were bonded to a balsa core. Internal spars and ribs were provided, and balsa leading and trailing edges completed the contour. The models were tested on a vibration table to demonstrate that vibration characteristics were satisfactory. A typical model was then cut into several segments. These were next weighed to check that the model's mass distribution was correct. Some models had extra skin to alter the frequency ratios in order to fully explore the flutter boundary. Strain gauges were used to record wing bending and torsion. The first series of tests was done on cantilever models mounted with an end plate to simulate the fuselage side. The tests were carried out at the Massachusetts Institute of Technology in Cambridge. The tunnel was a slotted wall blowdown type capable of speeds from Mach 0.7 to Mach 1.2. The operation is seen from this model. A pressurized low-speed tunnel is used as the air supply. The air passes through a control valve and a temperature stabilizer into the test section and finally out the exhaust stack. An air shaker was used to excite the wing modes for damping measurement before installation in the tunnel. The model was then installed on the tunnel sting, the strain gauge recording equipment connected, and the tunnel prepared for a test run. The first model showed no flutter, and weaker models were tested to establish the flutter boundary. As the tests proceeded, a model fluttered over a very narrow range, giving a lower limit to the flutter boundary. Weaker models showed the increasing flutter range. The slow-motion camera provides the indication of the flutter mode and indicates the rugged qualities of the models to withstand these forces. On completion of the cantilever tests, full-span models were built. To avoid choking the tunnel, the fuselage area had to be reduced, requiring external concentrated masses to simulate the engines. The wing construction was identical to the cantilever type. The model support allowed translation but was self-aligning to provide stability in pitch. The model was shaken to establish its frequency ratio and was then mounted on the tunnel sting. Tests once again established the flutter boundary. One model barely fluttered, and a weaker one fluttered over a wider range. The slow-motion camera illustrates how the fuselage bending mode becomes the primary flutter mode in the full-span configuration. Although the violent flutter caused some skin tearing, no models were lost during the testing. These transonic model tests demonstrated that the Arrow wing is flutter-free in the most critical region.